Welcome to the Peacademia course on the basics of semiconductors. This lecture will cover the electrical properties of materials. Let's start. By the time you finish this lesson, you will learn how to study the electrical conductivity using the energy band diagram, the temperature effect on the band gap, the generation and recombination processes, and the charge carriers, electrons, and holes. In the introduction lecture of this course, I asked a very fundamental question. What causes a material to behave as a conductor, semiconductor, or isolator? Now it's the time to address this question. In the previous lectures, I introduced the concept of the energy band and band gap, so we can use these concepts to discuss the electrical conductivity of materials. Since temperature affects conductivity and causes the generation and recombination processes to take place, I developed the discussion by this assumption that the temperature is set at 0 degrees Kelvin. I introduced the generation and recombination processes later in this lecture. As you recall, materials are divided into conductors, semiconductors, and isolators. For conductors, either there is no band gap between the valence and conduction bands, meaning the two bands overlap, or there is a band gap between the valence and conduction bands. However, the valence band is not fully occupied. As a result, a number of holes or states remain unoccupied. There are two charge carriers, electrons and holes. Both are causes of electrical conductivity. As a result, a not fully occupied valence band causes a material to behave as a conductor. Later in this lecture, I'll discuss the charge carriers, electron and holes in more detail. In semiconductors, the valence band is completely filled and has no empty states at 0 degrees Kelvin. Also, the conduction band is completely empty of electrons at 0 degrees Kelvin. A band gap also exists between the valence and conduction bands. Generally, we call a material a semiconductor if it has a band gap smaller than 4 electron volts. For example, silicon band gap at 0 degrees Kelvin is 1.17 electron volt. In isolators, everything is the same as semiconductors, but with one difference. Isolators have a very big band gap. In general, we call a material an isolator if its band gap is larger than 4 electron volts. The forbidden gap or band gap is a function of temperature. The band gap diagram can be drawn versus the temperature. Here you can see the band gap temperature diagram for the semiconductors, gallium arsenide, silicon, and germanium versus temperature. As you can see, by increasing temperature, the band gap gets smaller. If you remember the lecture of the energy band, you can tell why a temperature rise makes the band gap smaller. In fact, when the temperature increases, the interatomic distance increases. This brings the top of the valence band and bottom of the conduction band closer to each other. So the band gap gets smaller. Earlier in this lecture, I briefly talked about the generation and recombination processes. Let's take a closer look at these two. Imagine that we have a pure silicon bulk. The atoms have already created covalent bonds with each other. In this two-dimensional model, I'm just showing the valence shell of each silicon atom. At 0 degrees Kelvin, all the valence electrons are in covalent bonds, and as a result, there are no free electrons and holes. It is a good idea to also look at the energy band diagram. Since most of the holes are accumulated right under the top of the valence band, and all the electrons will be right above the bottom of the conduction band, I can just draw the top and bottom of the valence and conduction bands respectively. When the temperature is increased, let's say to the room temperature, the band gap decreases and electrons gain energy and start to wobble. As a result of this energy, some of the covalent bonds are broken. A broken covalent bond yields a free electron and a hole. This process is called generation. So in the generation process, two kinds of charge carriers are generated, electrons and holes. If the temperature is raised even more covalent bonds are broken and therefore more free electrons and holes are generated. When a hole is generated, if an electron comes close to the hole, it falls into the hole. This process is called recombination. In equilibrium, the generation and recombination processes are happening all the time. When a recombination happens, a generation happens too. This is because when an electron leaves its original place to fill an adjacent hole, a new hole is generated. Let's get back to this statement that both the electrons and holes are considered as charge carriers. Although it is crystal clear for a free electron to be considered as a charge carrier, it is not for the hole. A hole is simply a vacant site and a product of a broken covalent bond, or in other words, the generation process. This vacant site or hole does not move. So how are we considering a hole as a charge carrier if it does not move? To show it, let's assume no generation has happened yet to these atoms. After some time, a temperature rise causes a covalent bond to break. Now we have an electron and a hole. The electron story is clear. It can now move freely in the material. My focus hereafter is on the hole. Since the temperature has raised, the valence electrons are wobbling. If a covalent bond near the first hole generated is broken, a free electron comes close to the first generated hole and it is seized. Now you can see that the hole position is kind of moved. This process continuously happens in the material at temperatures larger than 0 degrees Kelvin. This animation shows the rest of the story and the way the hole is moving in the material. In this lecture, I discussed the electrical conductivity of materials and introduced the generation and recombination processes and the two charge carriers, electrons and holes. In the next lecture, I will talk about the direct and indirect semiconductors. Thanks for joining this lecture of Peacademia.